Alright, so today we're going to derive the quadratic formula, which was one of the most famous formulas in math that we use to solve quadratic equations. Alright, so we're going to kind of write a proof. Maybe you wrote some of these in geometry, but we're going to actually write a proof, and the math is already done. We're just going to write the justification of each step. So, as always, we start with the given. So, we're given a trinomial, and it's equal to 0, so we have everything on the same side. And then it looks like we subtract c, which is the subtraction property of equality. It says if you can subtract as long as you do it on both sides, you've maintained balance. And then similarly, it looks like they divided everything by a, so that's the division property of equality. And then this step right here, they're actually using the addition property of equality. We can add anything we want to both sides of an equation. So that's the justification of what they're doing. And then we need to think, why did they pick this? Why did they pick b over 2a squared? Well, it's because they're completing the square. If you recall, if the leading coefficient, this number right here, is 1, so if you have like 1x squared, then your c value can be written as b over 2 squared. And if you do that, then you will have a perfect square trinomial. The only thing is, this doesn't say b over 2 squared, it says b over 2a squared, so how did that a sneak in there? Well, remember, b is just a representation of whatever coefficient is in front of x. So currently, it's not just b in front of x, it's b over a. So like that collectively is your b value. So if we take that b over a, and then we're supposed to divide that by 2, seen right here. That's the same thing as doing b over a times a half, and that's going to get you b over 2a. So that's where they're getting it from. They really are using this formula. It's just that this is what they have in the parentheses because they had an a in the denominator to start that process out. And then if we look in the next step, it looks like the left side didn't change at all. It looks like they did two things here. They distributed this exponent, which is an exponent multiplication rule, and it looks like they went ahead and got common denominators. So it looks like they multiplied the top and bottom of this fraction by 4a. So I actually see two justifications, two things they did. They used an exponent multiplication property, which is when you distribute an exponent into a product or a quotient. And they also rewrote their fractions so that they could have common denominators. And then it looks like they did two things. They changed the left side into this format. So these are equivalent. This is the trinomial version of the area, and this is the factored version. So these are equivalent in value. If you FOIL this out, you will get back to this. And it looks like if you have the same denominator, you can go ahead and rewrite this as one whole fraction. So it looks like they did a few things, and I'm just going to simplify it to say they changed their trinomial to factored form, and they also consolidated their fractions. I do see a little bit of commutative property because it looks like they switched the b squared and the minus 4ac. If you notice, they switched order. That's called the commutative property, but we'll just say that that was part of their fraction consolidation. And then it looks like we're going to square root both sides, which is the square root property of equality. And then it looks like they moved over this b over 2a, and it looks like they actually they divided this into the square root of the numerator, and they actually did the square root of the denominator. So I'm going to go ahead and classify that as they used the subtraction property of equality, and they also did some radical simplification. Now I realize this may look confusing because you're like, well, isn't the square root of 4a squared just 2a? It's actually 2, technically it's 2 times the absolute value of a. And I'll actually go over that in a second as to why that's the case. You really don't have to worry about that so much right now, But if you take some higher math courses, you may see something like this in some theorems, so it's worth going over for a couple minutes. And then what we'll do is we'll actually find out that this will actually come out to be 2a. So you can just rewrite this all as one fraction. So we have another fraction consolidation. And this right here, that is the quadratic formula. All right, so let's investigate this whole absolute value business. Like, why do they have that in their proof? Let's consider if a is -1. Now, if this a term, if that's positive, you're not going to have any issues. But if it's negative, that's when you can run into a little bit of a danger zone. Technically, if you're going to do the square root of a squared, well, you would substitute -1 in for a. And if we do -1 squared, we get +1. And according to PEMDAS, you're supposed to work inside the radical first and then apply the radical as the last step. So we have to follow PEMDAS here, and we're going to get the square root of 1, which is 1. So if a is -1, then the square root of a squared is +1. So we just went through and justified that. Here's where you run into some trouble. Sometimes we like to think, well, you know what? A root and a square basically cancel each other out, right? So I can just rewrite this as a. And if this was like, 3, the square root of 3 squared is 3. So that's true. This was 4. Square root of 4 squared is 4. That's true. Again, the issue is with negatives. So according to our work, the square root of a squared could be a, but a is actually equal to -1. Hold on a sec. We just proved that the square root of a squared is +1, and now we're saying it's -1. So this is actually a little bit of a danger, because when you have negatives, you really got to follow that PEMDAS order. So just to make sure like all of our scenarios are considered safe, technically the square root of a squared is the absolute value of a, because that would change our -1 into +1. So by using those absolute value bars, we're acknowledging that PEMDAS rule if a is a negative number. It's kind of abstract, and I do get that it's a little confusing, but that is the reason that they have that in that formula, is to avoid getting two different answers for the same problem. So then, okay, well, why did they get rid of, why did they combine these? Like, this says 2a and this says 2 absolute value of a, so how's that going to work? So I look at an example. All right, again, let's consider if a is -1. I'm going to put -1 into the quadratic formula right here. All right, so I'm just going to plug -1 into the bottoms here. I'm not going to worry about it up top because I'm really more worried about the bottom. I'm going to do a little bit of simplifying. I get -b over -2. And over here I get all this stuff on top of +2, because 2 times the absolute value of -1 is +2. So then we're thinking, well, these denominators are different, so how can you just go ahead and consolidate these fractions? So remember, you're allowed to multiply the top and the bottom of a fraction by anything you want. So if I wanted to put these guys together, I could just multiply the top and bottom by -2, because now my denominators are the same. And all I have to do is just put this -1 right out front of my parenthesis, and that's what I did for this step. So I just multiplied this and this by -1. In doing so, though, I have a common denominator, and I get that common denominator is -2. So I'm just going to kind of consolidate this. And this is kind of weird. We typically don't write -b plus or minus negative root b squared. We have a little bit of extra signage going on. Because remember, plus minus means, hey, let's write it with just the plus, and then, oops, let's write it with just the minus. So we're going to consider the first scenario where we have -b plus negative root b squared minus 4ac. All right. Typically in math, we don't say like, oh, -5 plus -3. We just say -5 minus 3. So you don't really need to have plus negative, you can drop the plus. And then case 2, we would write -b minus -3. root b squared minus 4ac. But we know that when we subtract a negative, that's really just like adding a positive. So if you look, these are the same as what I have right here. This is true. 2a would get you negative 2, which is what I have. And it doesn't really matter about this absolute value because you're going to have a plus minus. All that's going to do is just change whatever sign you have, but you're still going to have a plus and a minus. So you're not going to be asked to prove this or anything, but that is what their logicality is. That's how they're getting at that formula. So I just want you guys to know that the quadratic equation, the quadratic formula, is derived simply by completing the square. We use a, b, and c instead of actual numbers to do that, so that we can use it for any situation. But it comes from completing the square. So summarize all the techniques that you have to solve quadratics. We do have graphing, but we very rarely use it. We're just more concerned that you realize that roots, aka zeros, are also called x-intercepts. As long as you know that, and you know that, okay, that's the solution to a quadratic, you're okay with graphing. We have a square root method, which is always the fastest method, but obviously it has to be set up so that you can use the square root method. So sometimes it's not applicable because it's not set up to be used. Then we have factoring, which is going to be probably the second fastest after the square root method. But that's only, I think, if a is 1. So if you have 1x squared, factoring will be very, very fast. The only problem is you may not find those magic 2 numbers that complete your x, and you may get stuck. But it's always worth giving it a shot. In my opinion, if a is not 1 and I cannot use the square root method, I have to go with complete the square quadratic formula. The only downside to complete the square, like, it's always usable. You can use it in any situation, so you'll always get an answer. But it's not very convenient if your leading coefficient isn't 1. So if you have like a 3x squared, you have to divide everything by 3. Then you might have some fractions, and that's where I see mistakes start to happen. So it's a little risky. I think the most beautiful way to solve is the quadratic formula because it's a formula. You just substitute variables, values for variables. So it's a modified version of complete the square. You can always use it, so it's just as reliable, but it's way more convenient if a isn't 1. So these are the techniques that you have. We will not use graphing, but we will use these 4 methods. So it's up to you to look at a problem and decide which of these methods do you think would be most appropriate. And then I just have the definitions. We're going to jot down the quadratic formula. Yes, it has to be memorized. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So if you have that memorized, you can solve any quadratic using that formula. And then we have a new word, discriminant, and that is whatever is under the radical in the quadratic formula. So the discriminant is whatever b squared minus 4ac is. Whatever that number is, that is called the discriminant. So a fun fact for you, if your discriminant, so if this comes out to be a perfect square, that means that you really could have factored the problem. It would have factored nice and pretty for you. So again, just a fun fact. So that's a little trick that I use when I am running a scenario through my head real quick to see if the X method will work. I do this real quick in my head and I get my answer. The discriminant does have some values to it. One of them is it tells you how many solutions and what type of solutions you'll have, so you can kind of predict like the outcome of what you're going to get when you solve. So I'm going to stop here because I'm pretty sure this video is longer than I would like it to be, but the next video we'll go ahead and we'll do some practice solving some random quadratics.